This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai's studies. A link is in the description box below. Does the following series converge or diverge? Well, the first thing you want to do is find out if this is a positive series or a negative series. So the question that you can ask yourself is, does this series contain negative values? Well, if we take a look at the numerator, we know that sine of anything is going to be between -1 and 1. And so therefore we know that this series is going to contain negative values, and therefore we establish that this is a negative series. And so that's a problem, because so far we've only learned tests for positive series. We know DCT, LCT, integral tests are for positive series. So we have a negative series, so what do? Well, we can just make it positive by adding absolute value signs around it. Just like you have -1, if you add absolute value signs, now it becomes positive. Okay, so we made the series positive in hopes that we're now able to use the tests that we learned, like DCT, LCT, and integral tests, on this series. But wait, doesn't adding absolute value to it make it a different series? Yes, that's why we call it the corresponding positive series. But wait, if this is a different series, then what good does it do for us if we're allowed to use a test that we learned on this series if they didn't ask us anything about this series? They asked us if this series converges or not if this one converges or not. So what good does it do for us to test this one if it's not going to tell me anything about my given series, since they're not the same? But here's a secret. Testing this corresponding positive series does tell you something about the given series. But what makes this part possible? What makes us connect these two series? Well, I call them the two tools in our toolbox when it comes to negative series. The first is a definition. The definition says that if the series with absolute value converges, therefore the given series converges absolutely. So if the blue series converges, then the given series converges absolutely. Why absolutely? Because it's saying if we find that this series converges, then we know that the given series is going to converge absolutely, because it literally converged with absolute values. And then the second tool in our toolbox is the absolute convergence theorem, which states that if the given series converges absolutely, then the given series converges itself. Let me give you some intuition behind this statement over here. It's kind of similar to the direct comparison test. So recall that this is just your series A of n, and so your corresponding positive series is literally just your series A of n with absolute value surrounding it. Now, if this is your series A of n, the worst that you can do when you add absolute value is have it be bigger. Let's say you have a series A of n. If you add absolute value to that, it's still A of n. But let's say your series was negative. If you add absolute value to that, it becomes bigger. So the least you could do is basically no change, have it be equal to each other, but the worst you could do is just make it bigger. So this series over here will always be bigger or equal to the given series. And so if we know that the series with absolute value is going to converge, meaning it's going to be limited to a certain value, and we know that this series over here is always going to be smaller than this one, so it's not like it could surpass it. And so if this converges, if this is going to stop, then this one will also have to stop and converge as well. Because again, it always has to be smaller than the bigger series, and we know that it cannot diverge, it can't surpass it. And so if the series with absolute value converges, is being limited to a certain value, then so will the given series have to converge as well and be limited to a certain value, because it always has to be smaller than the bigger series, so it can't surpass it. So it's going to have to converge eventually. So the whole idea is if we're able to test this corresponding positive series and we can find that it converges, then we can say that the given series converges absolutely and use ACT, the absolute convergence theorem, to say that because it converges absolutely, we know that it converges itself, and then we can answer the actual question. So let's go ahead and test this corresponding positive series. So just treat this as one of your regular positive series that you did in the beginning. So I look at this and I'm like, okay, which test am I going to use? Because now that it's positive, I can use DCT, LCT, integral. So which test am I going to use? Well, in my head, I see trig, and then I see a really nice simple n squared. So I'm thinking DCT or LCT first. And so then I ask myself, is there any way I can get a B of n? Because without a B of n, without anything to compare to, you can't use the comparison test, right? And so I remember that because I see trig, I know that that usually becomes a 1. So I have kind of an idea that this is going to become B of n. And so I'm going to try DCT, and I always do DCT before LCT. So what is the rule for the direct comparison test? And I always draw a picture if I forget. So I always have A of n, and we have B of n. If A of n is less than or equal to B of n, and the series B of n converges, then the series A of n will have to converge as well. And then the opposite. And so I, B, B, C, C. I stands for information. the information that we know plus the information that we need. And so the information that we know is that this is our A of n, our given sequence. And honestly, we don't need the absolute value for the whole thing because we know that n is always going to be equal to 1 or greater than 1. So we know that this can never be negative, but we do need absolute value around this because we know that this can be negative. Because sign of anything is between -1 and 1, so it could be negative. And then the information we need is our B of n. We don't know what that is. Well, that goes into our second step, which is find B of n. So the way I do this is I take my A of n, and I ask myself at large n, so basically when n goes to infinity, this becomes what? Basically, we're asking what becomes insignificant as n gets really, really big. Well, again, anytime I see trig, that just becomes a 1. And then we can leave the n squared because if we plug in infinity, that's obviously still going to be very significant. And so that is our B of n, which brings us to our third step, which is the behavior. So B for behavior. How does a series of B of n behave? The series B of n is from n is equal to 1 to infinity. I get these numbers from the original problem here. B of n is this. Remember, in this step, the only thing we ever use is either the geometric test or the p-test. So to find out which you're going to use, you want to recognize the form. To recognize the form, make sure you have this simplified. So I recognize that this is in the form of 1 over n to the p, where p is equal to 2. So I know this is going to be the p-test. The way that I remember the rule is PG-13, the movie rating. So p is greater than 1, forget the 3, and converges comes first for both tests, geometric and p-test. And then the opposite is true. And so I know p is equal to 2, which I know is greater than 1. So therefore, this series B of n converges. And so now this is one of my clues here. I go ahead and highlight this over here. And then now I'm hoping that when I check and compare A of n and B of n, I'm hoping that A of n is smaller than B of n, because if this is true and this is true, then I can say that this is true and I can get an answer. Which brings us to our next step, which is C for compare A of n and B of n. So my A of n is this. Put a little circle here. My B of n is this. By the way, technically it was absolute value of 1, but then absolute value of 1 is 1. And now I compare. So which one is bigger? Well, they both have the same denominator, so you're really only comparing the numerators. And we know that sign of anything is always between -1 and 1. And also remember that there's a hidden 0 here. We don't ever put this because we all assume that everybody knows that DCT, LCT, and all these tests only work with positive series, so series that contain terms that are greater than 0. So this -1 is irrelevant, especially because it has the absolute value, so it can never even be -1. It's going to be always positive. So therefore, the worst that it could be is less than or equal to 1, because the max it can be is 1. It can never be greater than 1, and it can still be less than 1, but not negative, because we added an absolute value sign around it. So therefore, our A of n is less than or equal to our B of n, and that's our second part. So now that I know that this is true, I just proved it, and I know that this is true, then I can say that the series A of n converges. Which brings us to our last step, which is C again, but for conclusion, where we wrap everything in a nice sentence. So we start with since, and then I go in the order of my work, so blue and then green. The series B of n converges by the p-test, where p is equal to 2, which is greater than 1. And then my green part, I literally just copy this. And I say for all n is greater than or equal to whatever number is in the original problem, so that's 1. The direct comparison test implies that this series, this is where it's different, this series, the corresponding positive series converges. I'm going to write it down so you can see it. This one converges. And so we're using our number one tool here, which is our definition. If the corresponding positive series, which is just a series with absolute value, converges, then therefore the given series converges absolutely. So which implies the given series, and then I'm literally going to copy and paste the given series, converges absolutely. But remember, we don't care about converges absolutely. We just want converges or diverges. So that's where this second part comes in. If we know that a series, a given series, converges absolutely, then we can say that the series itself converges by the absolute convergence test. So if the given series converges absolutely, then we can say, and absolute convergence implies convergence. So by the absolute convergence theorem, the given series converges as well. And so this yellow part was really talking about the corresponding positive series, but then we use our two tools in our toolbox, the definition and then the absolute convergence theorem, to get the final answer, which is, does the given series, right, converge or diverge? And so the answer is that it converges. And honestly, I would remove the so, just so that it's clear that this is true because the absolute convergence theorem says so. So hopefully you see how I just proved to you that we can test the corresponding positive series, and that's going to tell us some information about the given series. We took the corresponding positive series, tested it, we found that it converged, and using our two tools in our toolbox, we derived the fact that the given series converged as well. So we got some information about the given series. And that's it for this video. I'll see you in the next.